And now for an exciting episode of Chemistry in Space.
Chemist's log. Stardate 12412.09. We have just returned from planet Joshua Tree, where the away team recovered the following two images showing areas of nebulosity in the night sky, one blue and one red. We are now submitting them for spectroscopic analysis.
Good afternoon, and welcome to Hand-Wavy Chemistry. Two of the best things about science are that it is repeatable and reproducible. Now, they may sound very similar, but they are subtly different. Repeatable means that I can do the same experiment over and over and always get the same result. Reproducible means that somebody else can do the experiment and get the same result. It doesn't matter if it's happening in my laboratory, your laboratory, here on Earth, or up there in space. During the introduction, I showed you two photographs of nebulae that I took at Joshua Tree National Park. The first was this blue one. It is a reflection nebula surrounding the star cluster known as the Pleiades. Light from those stars is being reflected and scattered by interstellar dust. The color relates to the size of the dust particles that are scattering the light. But that sounds dangerously like physics, so let's just focus on the other picture, the red one. In this case, the gas is being ionized by hot stars nearby. It's primarily red because there is a lot of hydrogen in the area. But if there were other atoms around, we could see different colors, like greens and blues. When we probe these colors, we see spectral lines. We see specific wavelengths of light that correspond to the atoms that are emitting them. This technique of looking at the spectral lines to identify elements is used all the time by analytical chemists, using procedures such as flame atom absorption spectroscopy or inductively coupled plasma atomic emission spectroscopy. And out there in space, it's not just limited to looking at what atoms are in hot clouds of gas. We can apply this technique to the stars themselves. Helium was first detected during a solar eclipse. Scientists analyzed the spectrum of the sun and observed spectral lines that corresponded to no known element. So they called it helium after the sun. And later, when a sample of helium was obtained on Earth, an electric current was passed through it, and it began to glow, and its spectrum was recorded. And it was found to line up exactly with those lines seen in the sun. Interestingly, when we look at distant stars and we look at their spectral lines, their relative position seems correct, but they are shifted, usually towards the red. This is direct evidence that the universe is expanding and that the stars are moving away from each other. It's like when you hear a siren. As it comes towards you, it sounds higher pitched, and as it goes away from you, it sounds lower pitched. A star is coming towards us. The light it emits will seem closer together, blue shifted. If it's going away from us, it will be red shifted and spread out. We can even observe the rotation of galaxies due to this phenomenon. We can look at one side and see that it's moving away from us, and then we look at the other side, we see that it's coming towards us as that galaxy spins and rotates. The other things we can look for in space are molecules. Infrared spectroscopy is able to identify the bending, stretching, and vibration of particular functional groups. And there are very well-known peaks and frequencies associated with OH bonds, NH bonds, and C double bond O, all of which are the kinds of functional groups that we would associate with life. The James Webb Space Telescope has been fitted with an infrared camera. One of the reasons for this is so that it can look at and probe the atmosphere of planets in other solar systems. When an exoplanet orbits its star, if it crosses between us and the star, it will block and obstruct some of the light from that star. And we will see this as a periodic dimming. This is one of the ways that we are able to detect planets outside of our solar system. However, when it is lined up and blocking light, it doesn't block all of the light. Some of it will go around, and some of it will pass through that planet's atmosphere. And as it does so, if there are infrared active molecules, they will absorb the light from the star. And so, by comparing the spectra of the star when the planet is between it and us, and when the planet is somewhere else in its orbit, we can begin to probe and understand what gases there are in that planet's atmosphere, and potentially spot some signs of life. What we should do if we detect possible signs of life on exoplanets? Well, that is a question far above my pay grade. I hope you have enjoyed this video, and if you have, please make sure to like, subscribe, and share it with your friends. And if there is a topic you'd like to see covered in a future video, please put it down in the comment section below. Thank you, and I hope you have a wonderful rest of your day.